Hello friend, good morning and welcome back to the third video lecture based on internal combustion engine performance and emission on EVM Tech Android. So this is the QR code of the channel and the channel name is EVM Tech Android. Either you can scan this QR code and you can see this video, or you can just type EVM Tech Android on the YouTube and you can take advantage of such free video lectures. So today we are going to discuss about theory related to the heat balance sheet. We are going to discuss about different method to measure the friction power, that include, you can say, Morse test, Williams line method, etc. So now we have to discuss about measurement of friction power. In the previous video lecture we had discussed about different performance parameters and how to measure these parameters, how to calculate some parameters. All this is available in the previous video, and the link for the previous video is available in the description box. So today we will discuss first about the friction power, how to measure the friction power. So what is friction power? So the difference between indicated power and brake power is a friction power. So if we want to differentiate between, you can say, a good engine and bad engine, we can easily differentiate, because if the friction power is less, it is a good engine. And generally what you can see, the friction losses are ultimately dissipated to the cooling system and in exhaust system as they appear in the form of frictional heat. So what we are talking about, the heat dissipation, and that heat that is carried by the exhaust gases or heat that is carried by the cooling system, that is nothing but a heat loss, or you can say that is a friction loss, which we are considering in terms of heat loss. So for this kind of system, definitely cooling system is required with very good cooling capacity. Moreover, if you go with the lower friction, means more brake power is available, or you can say more power is available at engine shaft, and hence BSFC, that is brake specific fuel consumption, is lower. So what is BSFC that we had discussed in the previous video lecture? BSFC, that is the amount of fuel consumed in kilogram per hour to produce unit brake power. And we had discussed brake power means the power available at engine shaft. So it is always desirable that the friction loss should be minimum 1. If the friction losses are minimum, it means engine is good. So these are 4 different methods to calculate what are the ways to find out friction power. First is the Williams line method, motoring test, Morse test, and the difference between indicated power and brake power. So out of all the 4, we have to discuss initially about all the 4, and at end we will conclude which method is suitable under which circumstances. So one by one we try to discuss about all the different methods. The question may be there in your internal test, in your university examination. It may be there in the gate examination. What are the different methods? Just write different methods to find out friction power, or in detailed description you have to write about the different methods, or you have to write just different method and you have to explain any one of these 4. This include Williams line method, Morse test, motoring test, and difference between indicated power and brake power. So first we try to discuss about Williams line method. So this is the Williams lines method. In the next slide we will discuss again in detail about the Williams line method. So in this method, a gross fuel consumption versus brake power at constant speed. This is a very important. We are talking about constant speed. So in this method, gross fuel consumption versus brake power, the graph of fuel consumption versus brake power at constant speed is plot, and the graph is extrapolated back to the zero fuel consumption. Means you can see the graph is plot, and now we are extrapolating this graph towards the other side. So what you can see, the point where the graph cut the brake power axis. This is, you can say, point where the graph is cutting the brake power axis is an indication of the friction power of the engine at that speed. The negative work represents the combined loss due to the mechanical friction, pumping power and blow by. So this negative loss which you can see here, this negative loss, this one, this is negative work available because of combined loss of mechanical friction, pumping power and blow by. So if we talk about the major drawback of this method, you can see the main drawback of this method is the long distance to be extrapolated from the data measured between 5 and 40% load towards zero line of fuel input. Means we have to go from, you can say, full load to part load, and we have to move towards no load condition. The directional margin of error is rather wide because of the graph, which may not be a straight line in many a time. This in the next slide we will discuss, if this graph is not a straight line, it is creating issue. The changing slope along with the curve indicate the part efficiency of increments of the fuel. The pronounced change in the slope of this line near full load react the limiting influence of air-fuel ratio and of quality of combustion. Similarly, if there is a straight curvature for a lighter load, this is perhaps due to difficulty in injecting accurately and consistently very small quantity of fuel per cycle. So if we see the next part, you can see always this is not a straight line, and if we are moving towards the positive y-axis, when this graph is intersecting, when we will expanding this thing, this is the point you can see where it cuts the y-axis. So you can see the friction in torque, you can see this is the value. So here you can see the graph on x-axis, the either you can see the brake power or engine torque is available, and on the y-axis the fuel flow rate in terms of gram per second is there. Here you can see engine speed is 1400 rpm, the jacket water temperature is 50 degrees Celsius, and you can see this is a graph. When we are extracting this graph, or when we are going for extrapolation of this graph towards a negative x-axis, when it cut the y-axis, you can see the next part is a friction power, and therefore it is essential that the great care should be taken at the light load to establish the true nature of the curve. When the system is at lighter load, the chances of error will be maximum 1. So now we will go with the next part, that is a Morse test. So what you will observe in the Morse test is, this Morse test is applicable only for multi-cylinder engine. This is a very important thing. When we are talking about the Morse test, it is applicable only to the multi-cylinder engine. The question may be there in the competitive exam, in the MCQ, if it is a single cylinder engine and if you want to go for Morse test, whether it is possible. No, it is not possible. So Morse test is applicable only for the multi-cylinder engine. So what happens in this test? The engine is first run at required speed and output is measured. Means you can say either you go for full load, part load or no load condition. We have to test the engine first at required speed, and we have to measure what is the output. After that, what we have to do, if it is a petrol engine, we have to cut, one cylinder is cut by short circuiting the spark plug. So if it is a petrol engine, we have to cut one cylinder by short circuiting the spark plug, or if it is a diesel engine, we have to disconnect the injector if it is CI engine. So if it is a petrol engine, we have to go for short circuiting of the spark plug. If it is a diesel engine, we have to go for disconnection of the injector. So what happens in this case is, one cylinder is cut from the system. Because of that, what happens under this condition, all the other cylinders motor this cutout and cylinder. The output is measured by keeping the speed constant as its original value. We have to keep speed constant. And initially we had measure what is the output of the engine when it is run at constant speed with all the cylinders. Now out of all cylinder, one cylinder is cut. Again we have to maintain constant speed and we have to measure the output. So initially one output is measured with all cylinder, and now one output is available with cutting of one cylinder. So the difference in the output is a measure of indicated power of cutout cylinder. Thus for each cylinder indicated power is obtained, and when we add all this indicated power, it gives the total indicated power of the engine. So initially, if you can say, it is a 4-cylinder engine. If it is a 4-cylinder engine, you can say what we have to do. Initially we have to measure output of all the 4 cylinder at constant speed. Then we have to cut one cylinder, so output is available of 3 cylinder. You can say we had cut the first cylinder, then we have to measure the output. We have to cut the second cylinder, we have to measure the output. We have to cut the third cylinder, we have to measure the output. We have to cut the fourth cylinder, we have to measure the output. So initially output is available for second, third and fourth cylinder, then 1, 3, 4 cylinder, then 1, 2, 4 cylinder, and then 1, 2, 3 cylinder. So you can see here same thing is mentioned. The indicated power of n cylinder is given by IPN, that is equals to BPN plus friction power. If one cylinder is cut, then indicated power of n minus 1 cylinder is given by indicated power of n minus 1 cylinder, that is equals to brake power of n minus 1 cylinder plus friction power. Since engine is running at same speed, it is quite reasonable to assume that the friction power remains same. So if we talk about equation number 17 and 18, if we'll go for subtraction of 7.17 minus 7.18, what we'll get? IPN minus, you can say this IP of n minus 1, because this friction power that will be cancelled. So what you can see, the IP of n cylinder, that is equals to BP of n cylinder minus BP of n minus 1 cylinder. So in this way we have to find out indicated power of each case. When we cut first cylinder, when we will cut second cylinder, when we will cut third cylinder, when we cut fourth cylinder, and we add this IP1 plus IP2 plus IP3 plus IP4, we will get what is the total IP of the multi-cylinder engine. The same thing is mentioned here. Total IP is available, that is IP of n, that is equals to IP of n cylinder, summation of all the cylinders. And when the brake power is available, when indicated power is available, when we will go for indicated power minus brake power, you can say friction power is available. So if we talk about this method is good enough, though it gives reasonable accurate result, and it is liable to error due to the change in the mixture distribution and other condition by cutting one cylinder. When we cut cylinder, there is change in some condition into the engine, that is distribution of the mixture as well as other condition when we will cut the engine. If we talk about petrol engine, what we can see is there is a common manifold for 2 or more cylinder. If we talk about multi-cylinder engine, and mixture is distributed, as well as volumetric efficiency, both will change. If we cut the one engine, you can say the way in which the mixture is distributed in the multi-cylinder engine and the volumetric efficiency both will vary. Again, almost all engine has common exhaust manifold for all the cylinder, and when you cut it out of, you can say 4 cylinder or 3 cylinder, if you go for cutting of one cylinder, it may greatly affect the pulsation in the exhaust system, which may significantly change the engine performance by imposing different back pressure. So if we cut one cylinder, the back pressure will vary, and when there is a variation in the back pressure, engine performance will vary. So again, it is like that, when you will go for cutting of one cylinder, what you will observe is mixture distribution will vary, volumetric efficiency will vary, and back pressure will vary. So these all are affecting again the indicated power value. Next is the motoring test. So what we have to do in the motoring test is, the engine is first run to the desired speed by its own power and allowed to run at given speed and load condition for some time, so that oil, water and engine component temperature reach to the stable condition. So this is a very important thing. Whenever we are doing any kind of performance in the laboratory, first is we have to reach to the stable condition. We have to run engine for some time, so that what is the oil temperature, water, cooling water inlet outlet temperature, exhaust gas inlet outlet temperature, all will reach to the stable state. And once the stable condition achieved, then we have to go for any kind of test. So in case of motoring test, what we are doing is, the power of the engine during this period is absorbed by swinging field dynamometer, which is more suitable for this test. So when we are going with this motoring test, we have to reach for the stable condition first, and then we have to we have a system with electric, this is swinging field dynamometer, in which the fuel supply is then cut off, and by suitable electrical switching device, the dynamometer is converted to run as motor to drive for motor the engine at the same speed at which previously it was running. So what we are doing, again you can see the fuel supply is then cut off, means initially we have to run the engine at one particular load at one particular speed, and then we have to cut off the fuel supply, and we have to, what we have to do, with suitable electric switching devices, the dynamometer is converted to run as a motor to drive for motor the engine at the same speed at which it was previously running. The power supply to be motor is measured, which is the measure of friction power of the engine. During the motoring test, the water supply is also cut off, so that the actual operating temperatures are maintained. So this is a very important thing. We have to cut off the water supply also. So we try to maintain the original operating situation. So in this motoring test, though determine the friction power at the temperature condition very nearer to the actual operating condition or operating temperature, at the test speed and test load does not give the true losses occur under firing condition due to the different reason. So when we are cut off the fuel supply, means firing is stopped, and when firing is stopped, what you can observe here is the losses observed under firing condition is eliminated. So again, when we will go for the motoring test, again the difficulty is observed. We are moving towards the actual situation, but in the difference which we will observe here is, in actual situation when the fuel is supplied in the multi-cylinder engine, there is a firing order set, and according to that firing is observed in the different cylinder. But when we will go for motoring test, what we will observe is the firing is missing, and because of the actual losses observed under firing, that is eliminated. So what you can see here, the different reason, the temperature in the motor engine are different from those when the firing is observed, because even if water circulation is stopped, the incoming air cools the cylinder. So when there is no firing, definitely the fresh charge is entering into the system, cylinder temperature is decreasing. This reduction in the temperature reduces the oil temperature and increase the friction, plus increase the oil viscosity. This is the problem that is much more severe when we'll talk about air-cooled engine. So when we cut the fuel supply, this is observed. Second thing, the pressure on the bearings and the piston ring is lower than firing pressure. The load on main and connecting rod bearings is also reduced because no firing, no excess temperature rise, no, you can say, valve formation. The clearance between the piston and cylinder wall is more because of the cleaning. This will reduce the piston friction, because when the temperature is reduced, the clearance that will increase. The air is drawn at a temperature less than the engine is when the engine is firing, because it does not get heat from the engine. So here we are talking about preheated air that is entering into the engine cylinder when there is a firing. Engine temperature is high, but when we are cut off the fuel supply, there is no firing, and because of that this is observed. And during exhaust, the back pressure is more, because under motoring conditions sufficient pressure difference is not available to impart the gases. The kinetic energy is necessary to expel them from the exhaust. So again, when we are not you can say creating exhaust gases because of burning of fuel into the engine cylinder, back pressure is vary, and because of this back pressure is not sufficient, again the performance is vary at engine exhaust side. So this way you can say major limitations when we'll go for motoring test. And the fourth method is difference between indicated power and brake power. So indicated power generally you can say that is available from the indicator diagram, and brake power that is obtained from the dynamometer. So directly we have to go for IP minus BP, that is the friction power. In obtaining the accurate indicator diagram, especially at high-speed engine, this method is usually only used in research laboratory. It is used at commercially level very limited. So for laboratory purpose, generally we go for IP minus BP, that is friction power, but when we will go for commercial level, it is not widely used. Now if we will go for comparison, or you can say when we want to go for conclusion of all the four different method, what is the conclusion? The Willan lines method and the Morse test are very cheap and easy to conduct. Moreover, both these tests give only overall idea of the losses, whereas the motoring test gives a very good insight into the various causes of losses and is much more powerful. So compared to the Williams line method and Morse test, this motoring test is a more powerful tool to analyze. As far as accuracy is concerned, indicated minus brake power, that is indicated power minus brake power method is more suitable or accurate if it is carefully done. The motoring method is usually give higher value of friction power as compared to that of given by the Williams line method. So according to our situation, out of all the four methods we have to select any one. So friend, now we will discuss about performance of petrol engine. So in case of petrol engine, when we'll go for performance, generally that is considered by heat balance sheet. And when we'll consider the heat balance sheet, the major components include the heat equivalent to the effective work of the engine, that is heat equivalent to the brake power, heat rejected to the cooling medium, heat carried away from the engine by the exhaust gases, and unaccounted losses. So these unaccounted losses include the heat loss by the radiation from the various part of engine, plus heat loss due to the incomplete combustion. The friction loss is not shown separately, because as the friction loss ultimately reappears as the heat carried by the cooling water, heat carried by the exhaust gases plus radiation. So in the heat balance sheet, what we'll observe is, we can see this part: heat equivalent to the break power, heat rejected by the cooling medium, heat carried by the exhaust gases from the engine, and unaccounted losses. So you can see the sample heat balance sheet. You can see on one side heat supplied, that is available in terms of, you can say, kilojoule per hour, or you can say in terms of kilowatt, and you can say it is also available in the percentage, that is, you can say 100%. So heat supplied, that is in the formula, that is mf into cv. In the next video lecture we have to solve the numerical, so at that time we will go for this heat balance sheet. This is one part, that is input part. Now what is the output part? So this is output part. So you can see here output part, that include equivalent to brake power, then you can say heat equivalent to brake power, then you can say heat carried by the cooling water, heat carried by the exhaust gases, and unaccounted losses. So again, that is in terms of kilojoule per hour and percentage. So you can say input, that is 100%, output, that is 100%. So we have to draw this kind of heat balance sheet when we want to measure the performance of petrol engine as well as of diesel engine. You can see here the same thing. If we go for the, you can say, table 7.1, you can find here in case of petrol engine and diesel engine what is the useful work. Then we can also find this is a useful work for you can say one engine. You can see heat carried by the coolant, heat carried by the exhaust gases, and unaccounted losses. So you can say out of 100% energy that is supplied, only 20 to 25% is utilized in terms of brake load efficiency or brake power. So 21 to 28% is the brake power or heat equivalent to the brake power, and in case of diesel engine it is 29 to 42%. In the similar way you can find out this is heat carried by the coolant in case of petrol engine, and this is for the diesel engine. This is heat carried by the exhaust gases for the petrol engine and for the diesel engine. So if we talk about unaccounted losses, you can see 3 to 55% unaccounted losses for the petrol engine, and you can see 21 to 0% that is for diesel engine. In the similar way you can see the different graphs that will be helpful when we'll go for analysis of a petrol engine or a diesel engine. You can see for petrol engine, this is the graph of brake thermal efficiency, that is eta THB, with increase in the RPM on x-axis efficiency will be there. Second is indicated thermal efficiency, definitely eta THI is more than eta THB. The specific fuel consumption you can see that is decreasing with increase in the speed, and after certain speed you can find again the specific fuel consumption start to rise. Particularly for petrol engine, when the speed is increased, you can see the mechanical efficiency is continuously decreasing. You can say around you can say 90% to it will reach to the 70%. So this is just a graph to give you a broad idea about how the efficiencies, specific fuel consumption vary with variation in the engine speed, and on the y-axis efficiencies are there. Now if we'll talk about the performance of the diesel engine, what you can see is, again for the performance of diesel engine, here initially only air is available and then the fuel is injected. So here the coolant loss is more at low load and radiation etc losses are more at high load. So coolant loss is more at low load, and if we talk about radiation and other losses are more at high load. So here if we talk about the brake mean effective pressure, brake power and torque that directly increase with increase in the load. So that we will discuss in the next graph or next figure. Unlike in petrol engine, the brake horsepower and brake mean effective pressure are continuously rising curves as they are limited to the load. The lowest brake specific fuel consumption and hence the maximum efficiency occurs about 80% of full load. So what we have discussed, around 80% will get maximum output, then there is variation in the output. So now here what you can see is this is a heat balance versus load for a diesel engine. So on the x-axis you find brake power is there, and on y-axis the percentage energy is there. So what you can see here is when the engine is running at 1200 rpm, the useful work that will be continuously increasing, it will reach to the peak and then it start to decrease when you can see the brake horsepower that is increasing from 10 to 40. Same is for the coolant, same is for the exhaust gases or radiation losses. So when the brake horsepower you can say that is less, means we are here around 10. You can see major component is this part, heat carried by the exhaust gases, where the maximum amount of energy that will be carried by the exhaust gases. And when we are around 25 brake horsepower, the maximum useful work is observed. These all are just a graph to show some nature when the engine is running at constant speed with variation in the load, and which kind of energy balance or which kind of energy loss is observed. Again, this is a graph of brake mean effective pressure, brake horsepower, brake specific fuel consumption, exhaust temperature, torque at engine speed 1500 rpm for a diesel engine. And again this is a graph for performance curve for GM 4-cylinder Toroflow diesel engine. So brake horsepower that is continuously increased when the engine speed is increased. Brake specific fuel consumption is decreased around at 2000 rpm, then again it start to increase. If we talk about the torque, with increase in the speed of engine the torque is increased, you can say up to 2000 rpm, and then it start to decrease. So this is just a nature of curve that is available with us when we'll go for actual performance on the engine at the laboratory or for the commercial use. These are some references, some websites, some textbook, reference books, and the website collection. You can refer, the same thing is available when you search on Google. These are some very good textbook for the IC engine, and these are some websites. So friend, we had discussed in general about what are the different ways to measure the friction power. We had discussed the performance for SI engine and performance for CI engine. Also we had discussed with some graphs about what are the different losses we will observe or how the energy balance or heat balance is observed. So if you like this video, then do not forget to press the like button. Also share this video and subscribe this channel. Again, the channel name is AVM Tech Android. This is the QR code of the channel. By scanning this QR code or just typing this AVM Tech Android, you can take advantage of such free lectures. Thank you. Thank you very much.